So friends, after doing the derivation for intensity for the double slit form of a diffraction, let us now go further into the condition for central maxima, minima and other things. First we will see the graph of intensity distribution. So this is how the intensity is distributed for the double slit experiment for Fraunhofer diffraction. You can see this is the maximum intensity curve. This point is the secondary minima. These are the secondary maxima, and hence like this it proceeds in both the side. So here the first factor in the formula that we have previously derived. Previously we have seen that the intensity distribution, that is I equal to 4I naught into sine square alpha by alpha into cos square beta. Here we know that the first factor, that is sine square alpha by alpha square of equation, gives the diffraction pattern due to a single slit, whereas the second factor cos square beta corresponds to the interference pattern produced due to both the slits. So if we write only this factor is for a single slit, and this factor will be factor for both slits in case of double slit Fraunhofer diffraction. Now, since we have understood this curve, we will now proceed to the condition for central maxima. So central maxima. We know that the intensity for the central maxima is the maximum, hence it is called the central maxima. Therefore, here theta will be equal to 0, as I have done before for the single slit diffraction. This is for the undeviated ray. This is for the undeviated ray. Here alpha is equal to 0 and beta is equal to 0. Why beta equal to 0 and alpha equal to 0? Since limit alpha tends to 0, sine alpha by alpha will be equal to 1, and since beta equal to 0 and alpha equal to 0, cos 0 will be equal to 1. We know from the values of trigonometry. Therefore, the intensity of the central maxima, if we consider to be I dash, it will be 4 into I naught. These terms are 1 and this also 1. So it will only be this term. So the value for central maximum intensity is I dash, if we consider it as I dash, that will be equal to 4 I naught. Number 2 will be condition for minima. There will not be a central minima, but we can call it secondary minima. For the diffraction minima, the intensity or I is equal to 0. That is, this portion intensity tends to 0, or it is absolutely 0. So we can see if it is 0, it is because of sine alpha equal to 0, or we can say alpha equal to plus minus n pi, where n is any number, that is 1, 2, 3, and hence goes. Therefore, that is a sine theta n equal to plus minus n lambda we can write. Why we can write this value? Because we know that alpha equal to pi a sine of theta by lambda. Therefore, again, for intensity minima, this was the value for alpha and sine alpha. Now we will proceed to this function, or cos square beta. So beta will be equal to plus minus 2n plus 1 into pi by 2. Why we will get this value? As we know cos squared beta to be equal to 0. Therefore, a plus b sine of theta n is equal to plus minus n plus half. We are getting from here n plus half into lambda. So we got this value. This is important to remember. And we got this value for central maxima. Hence, we can say the condition for maxima. The condition for maxima. What is the condition for maxima? A plus b sine of theta n will be equal to plus minus n lambda. So this is the important condition for occurring of a maxima, and this is the condition for occurring of minima. Remember this value also for sine, and this value it comes to be n plus half into lambda. So we have just calculated or derived and seen the distribution curve of intensity and derived the condition for central maxima, minima and other minimas. So friends, now we will move on to some further definitions of this module. We will see what is missing order. The definition of missing order comes in exam. So what is missing order? We can also write it as interference maxima, or it can also be defined as effect of increasing the distance between slits. So it is the effect of increasing the distance between slits. So shortly, missing order or interference maxima can be defined as the effect of increasing the distance between the two slits or the number of slits. So friends, this conclusion is very important for missing order. Let me read it out for you all. If conditions for diffraction minima and the conditions for maxima, that is diffraction maxima, of interference pattern are satisfied simultaneously for similar value of the angle of diffraction, that is theta we have considered, then the corresponding interference maxima will not be visible due to non-availability of light at that precise position. So this is what is called missing orders. So the suppressed peaks, that is the peaks or the maxima that get suppressed due to the non-availability of light at that point, will be called as missing order or interference maxima, or which we can shortly define as the effect of increasing the distance between the two slits. Now let us move further to the definition of what is a grating. What is a grating? A grating, or generally called as n number of parallel slits. So the broad definition of grating is that it is an arrangement. Let me write it for you for your convenience. The arrangement which consists of a large number of parallel slits, very minute parallel slits or very fine parallel slits they are, which are of equal width. It must be of equal width and separated from one another by equal opaque spaces. So friends, always remember the definition of grating. The broad classification or example of a grating is that we use in our daily life. If a substance is like this, it can be called as a grating. But for to be a grating, the substance need to have these slits of equal opaque spaces. What are equal opaque spaces? The space between two slits, that is from here to here, again from here to the next slit. These spaces are opaque spaces from which light cannot pass, and the width of the slits must be same. This arrangement is called diffraction grating. So now, after knowing the definition of grating, let us understand the definition of two different types of grating. Can be divided into two types. Number one is the transmission grating, and number two is the reflection grating. So what are the basic difference between transmission and reflection grating? So what is a grating? A plane transmission diffraction grating is an optically plane transparent glass. So diffraction grating is basically what? An optically plane transparent glass material on which equidistant extremely close grooves are made by ruling with a diamond point. So here, as I have drawn the small diagram in the previous page, like this the surface is present in case of a grating. Here equidistance is the slits from one another, and the width of the slits are also similar to one another. These slits are drawn by diamond ruling, since diamond can cut a glass material. So this is in case of transmission grating, but when the ruling is made on a polished metal surface, when the ruling is made on a polished metal surface, it is known as reflection grating. So this is the basic difference between transmission grating and reflection grating. Now let us see the diffraction by a plane transmission grating or diffraction at in parallel slits. This transmission grating can also be named as in parallel slits of equal width and equispaced. Remember, the derivation of this in parallel slits intensity and the further derivations are not required for the examination point of view. You only have to memorize the formula. So the intensity formula for in parallel slits will get modified into this. I, that is the present intensity, that is equal to I naught as previous, then sine square alpha by alpha square as the previous formula into sine square in beta. The n is the new term included due to n numbers of diffraction grating, by sine square beta. So this is the modified formula for intensity over n number of grating. So for a single slit, what will be the case? N will be 1, and for double slit experiment, N will be 2. Hence, you can only memorize this formula. Now, what will be the intensity of the principal maxima? Let us see the modified formula for intensity of principal maxima. What will be the formula for principal maxima intensity? The condition can be satisfied as d sine theta n equal to plus minus n lambda. I am not doing the derivations because they are not included in the syllabus. You only have to memorize the formula. So if this condition we can get in the problem, then it will be the condition for intensity of principal maxima. After this, let us see the second part, that is secondary or subsidiary maxima or minima. The secondary or subsidiary maxima or minima. So what will be the condition? For secondary minima, the condition will be d sine theta equal to p by capital N lambda, that is we can say plus minus p by capital N lambda. As because sine of, first you will remember this formula. Now I am telling you the reason why this occurs. We know the sine of n beta equal to 0 from the previous equation, or we can write, it will be only n beta equal to plus minus p into pi. We are considering p here, therefore from here this condition arises. Now for the maxima case, here we can see that there are n minus 1 number of secondary maxima. Therefore, the condition must be di by d of beta equal to 0. So if we differentiate, we will get n into tan of beta equal to tan of n beta. So this will be the condition for secondary maxima. Now let me write down the formula for two important topics. These are not so frequent in exam, but the formula can be useful. That is absent spectra and dispersive power of a grating. So the formula or the condition for absent spectra will be A plus B by A, that is equal to N by M. This condition we have reached from A plus B sine of theta n equal to n lambda, and we can write A sine theta n equal to m lambda. the derivation is not required. Just remember these three formulas. For dispersive power, the formula is d theta by d lambda is equal to n by a plus b into cos of theta. So for dispersive power of a grating, remember this formula. So now another formula I am writing for the examination point of view, the maximum number of grating spectra. The grating equation, we know that it is a plus b sine of theta n equal to n lambda. This is the grating equation, from where we can get n equal to a plus b sine of theta n by lambda. I am writing these with a different color because all of these steps are formula itself. Therefore, n max will be equal to a plus b into sine of 90 degree by lambda, that is equal to a plus b by lambda. This is the ultimate formula for n. Since the maximum possible value of theta equal to 90 degree, that is normal direction, the maximum number of grating spectra we can consider by considering this 90 degree here. So now we focus on another criteria, that is the resolving power of an optical instrument. So what is resolving power? Let me read the definition for you all. The process of separation of two very close objects by an optical instrument is known as resolution. And the ability of an optical instrument to resolve the image of two nearby objects is termed as the resolving power. So this is only the important definition from examination point of view. Now, what is resolving power for a grating? The ability to just resolve two nearby spectral lines so that the two lines can be seen separately. That is, the two nearby spectral lines need to be separated or resolved so that they can be understood separately, or their significance can be understood separately. So that is the resolving power of a grating. So these are two important definitions from examination point of view. Now let us understand what is Rayleigh's criteria. When central maxima of one source coincides with the first minimum of the other, if there are two or more sources, the two diffraction pattern will with equal intensities of two nearby sources will be just resolved. So this criterion is known as Rayleigh's criterion. One few example is drawn in below in the small graph that you can see here, the coincidence of the two graphs or two interference patterns in physical significance from two sources. So Rayleigh's criteria will take place in case of two or more sources. Now let us come to the last but one of the most important formula of this chapter and of this module, that is the resolving power of a grating. So the formula for resolving power of a grating will be lambda by d lambda is equal to small n into capital N. This is the formula for resolving power of a diffraction grating. With this, we have come to the end of this topic of diffraction and also of this module. Let's meet in the next module. Thank you.